goal is to be able to describe motion in terms of the unit tangent and the unit normal. So let's start with two-dimensional motion for a moment. Okay, I'm in a 3D world, but I'm moving around the room here. So I have a horizontal surface. I'm not going up and down. I'm moving around on the XY plane. So at any moment in time, if I'm not going on a line, then there's two things involved. There's the unit tangent and the unit normal. So if I'm talking about, if I'm moving along a curve, there's my motion. Then the unit tangent, let's say at this point right here, let's say that vector's of length 1, that vector's of length 1, they're orthogonal. This would be the unit tangent, this would be the unit normal. As I'm moving around, I can always describe my motion in relation to those two. So it's basically like I have these two vectors at all times when I'm moving. Okay, that's what it would look like. And this guy is always pointed towards the center of the circle of curvature. So if I did a tangent circle, okay, then we talked about the curvature of this circle and the radius of this circle and so on. The tighter the motion, the smaller the circle, the greater the curvature, and so on. So what I'd like to be able to do is to describe the acceleration in terms of T and N. I want to write something like this. I'll just generically say, okay, what letters of the alphabet? I'll say little c times t plus little d times n. Let me write it like that. That's the unit tangent, that's the unit normal. C and d would just be coefficients, and that would be the acceleration vector. We're going to basically figure out how to find C and d today. That's our main goal, because last day we figured out how to find the unit tangent and the unit normal. So now if I'm moving on a line, then all of my motion is in the direction of the unit tangent, and that d would be 0, and acceleration would just be a multiple of the unit tangent. If I was moving completely on a circle, okay, then there would be nothing in the unit tangent direction. So in that case, c would be 0, and a would be a constant multiple of the normal vector. Now, remember I said last day, all motion is linear, circular, or somewhere in between. So let's talk about all the somewhere in betweens today. I'm moving along a curve. It's neither a line nor a circle. So I'm going to have parts of both. So depending, the straighter that I am, the more is going to be in the tangent direction. The more circular I am, the more in the normal. So the size of the coefficients kind of dictate the shape. Again, more curvy, D is bigger. More straight, C is bigger. That's actually pretty simple to think about. Now, if I'm moving in 3 dimensions, the same thing holds true. And what I would always look at is, in my motion, I'm still going to have a unit tangent and I'm still going to have a unit normal, and they live on the same plane. But there's actually a third variable. Okay, you can see these. I've got three vectors here. One's coming out at you, one's up and down. And as I move through space, okay, I'm moving through space, there's always going to be 3 vectors, because there's also going to be one that's pointing upwards. So right now, as I'm moving on the plane, there's a vector that's pointing vertical and it's staying vertical. These guys are changing, but there's one more coming out at you. That's actually called the binormal. It's not important in our class. If you're an engineer, it's hugely important. Your 3rd-year engineering courses over at San Diego State, they're going to talk about the binormal. The binormal basically is the cross product of T and N, just so you know. It's a unit vector in the direction that is orthogonal to the plane that T and N live on, which means it has to be at their cross product. It's kind of a cool concept. We don't touch it in this class because that's not our emphasis. But in 3-dimensional motion, there must be a 3rd vector, because I'm also moving up and down, and that helps describe that. We're only interested in, as I'm moving, even in 3D, there's always a plane that T and N live on. So the circle that we're talking about is also on that plane. So if this curve were coming out at the board at you, there's still one T and one N, and they uniquely determine a plane, and we're going to go from there. So the question is, how do I find these pieces? And that is the question of the day. Well, last day, I introduced curvature, and we figured out an alternate way of describing curvature. very specifically using cross products and things like that and magnitudes. And it was a very, very simple thing. I'm going to review a little bit of that today as we go on. So today, let's start with the idea that, okay, I've got somebody just squeaked. I've got an R of t, which is, of course, x of t, y of t, z of t. Okay, we know that v of t is dx dt, dy dt, dz dt. And of course, then a of t would be each of those second derivatives. I know that, but the problem is those things might not be as useful because these pieces don't tell me directions. They don't tell me where I'm going next. Now, all motion, okay, let's make it just you. You're going to just walk around randomly. But if I could have a curve that describes your motion, better yet, if I could actually model it and have a vector valued function that describes your direction, your position at any given time, as I mentioned last day, if I'm looking with blinders straight forward at all times, then I am always looking in the direction of the tangent vector, the direction I would slide. But if I'm going around a turn and I'm on a bike, I'm in a car, and I'm looking straight forward at all times, I am not seeing where I'm going until I'm actually in the process of turning. That would be kind of dangerous. So when you're driving that car and you're getting ready to turn, your head automatically starts looking in the direction you're about to turn. And if I'm turning a sharp circle, I'm probably looking somewhat sideways. In other words, it's natural to automatically look in the direction of the acceleration. So if I'm going around a curve, it's almost like I'm looking at the center of the circle of curvature to some degree. If I'm on a line, nobody looks sideways when they're on a line. You look straight forward. So these might be correct if I gave you this in function form, but what if I said, okay, I want you to go in a general that way direction at a certain speed, and then I want you to maintain, I'm out in the real world. I'm not giving you a vector with brackets and functions in it. So we have to be able to describe it in every conceivable way, knowing the bits and pieces that go along with it. So let's start with, sorry, I'm finding a good pen here. Let's start with what we did last time. We know that the unit tangent vector is 1 over the length of the velocity vector. And I'm going to leave, these are all, it's implied all of these are functions of t, of time. That's implied. So I'm going to just not write t of t or, everything of t as we go. It just takes a little bit longer. It's implied that these are all functions of t. So what does that mean? Well, this implies then that v must be this, or this, because we know that the length of the velocity vector and ds dt are both exactly the same thing. We proved this last time. They're both called speed. Okay, there is no difference between them, except it's harder to do the calculus on this. It's easier to do the calculus in this form. So the next thing I want to do d dt. Where are we? I'm going to do d dt to both sides. So if I said dv dt, which of course is the acceleration vector, that would be d dt of ds dt t. Okay. If two things are equal, then their derivatives are equal. This is a scalar valued function. This is a vector, but they're both functions of time, which means I actually have to use a product rule. This is like a coefficient, but because it is a function, so, excuse me, so I'd have the first times the derivative of the second, okay, plus the second times the derivative of the first. But I'm going to write it in this order because you don't put a vector in front of a quantity ever. There was no notation for that. If I had said 4 times vector t, you don't write t times the scalar 4. That don't work. All right, so this is the acceleration vector. So there's no question about that. I've got that sitting there right in front of me. He said, well, that's really exciting. So what can I do with that? Well, actually, there's a lot I can do with that because we know something about this guy. It's related, this guy here is related to the unit normal vector. So I am going to go ahead and erase this stuff up here because I no longer need it. Now let's remind ourselves of a couple of things that we explored last day and that we discovered. And one of them is that we know that the unit normal was the unit vector. If you remember, it was the unit vector in this direction. So it was 1 over its magnitude. Okay, we know that. So then that makes, what does that make dt then? Okay, then doing like what we just did a moment ago over here, that means that this guy here is magnitude dt times the unit normal. Now, why is that important? Because I can insert that right here. And now what we'd have is we'd have a number times the unit tangent and another number times the unit normal. Now we're not done, but this is where we're going from here. Okay, so that's the first piece of the puzzle. So now the next piece is, what is that quantity exactly? Well, if you remember from curvature, let me erase this now. All right. We figured out that curvature was this length here over the length of the velocity vector. Okay, this is one of the things that I didn't tell you this, we discovered this when we were doing it. So again, that would mean that that length right there is nothing more than k times the length of v. But let's write it in this form so that it matches the other terms. So whether we write k ds dt or ds dt k, it's actually usually easier just to write it this way, ds dt times k. Oh my goodness. Okay. So going back to this, I can replace dt dt, the vector, with this magnitude times n. But we just found out that this magnitude is ds dt times k. So that means this is ds dt times k times n. These are both scalar valued functions. Now, when I say scalar valued functions, again, it means it's a function that when evaluated is a scalar. Aren't all functions when evaluated scalars? No, functions of more than one variable aren't scalars. If I have a function of more than one variable and I evaluate it at one variable, I still have a function of all the other variables. That's common in statistics and different things. We have a function of one variable, so when it's evaluated, it's now a scalar. Now, generally speaking, when we're doing problems like this, we're not really interested in an answer that's a function, because I want to know what is the acceleration at that particular time. What is the curvature at that particular point or that particular time? We're usually not doing these as functions. We're usually doing these at specific values. So that really would end up being scalar vector. So now with that, anybody see this? I can now rewrite this as A equals. Now, there's no good reason, but traditionally we put the unit tangent first, followed by this. Again, no good reason. That's just kind of the convention. So I'm going to write this one first. D squared S dt squared times the unit tangent. So that's a scalar times the unit tangent, plus ds dt k, and I already had a ds dt. So that's the square of the speed times k times n. And this, folks, is the magic equation that we're trying to derive today. This is the equation that governs all motion in 3 dimensions. All motion. Think of that. That's kind of cool. It's a scalar multiple of the unit tangent plus a scalar multiple of the unit normal that involves speed and curvature. We're not really sure what that guy is, but we'll figure that out. Now, we give each of these pieces names. And by the way, all of the development of what I'm doing today is on pre-printed notes. So you can go back over the notes, and I have lots of examples on the notes. I'm not going to go through the examples from the notes. I'll leave those to you guys. So with this statement here, we generally, this is the rule, so we generally name these guys. We call d squared s dt squared, which basically is the derivative of speed. We call this a with a subscript of capital T. That's not a vector. This is called the tangential component of acceleration. Then that guy there, the square of the speed times curvature, we call that a little capital N. And that is called the normal component of acceleration. Okay. So our goal is then to calculate each of these two independently if we can, and then, see if we can express this. Now, in this process, we usually don't bother actually finding the specific capital T and the specific capital N. And wait a minute, don't I need to find exactly what the unit tangent? Yeah, but if I already have the unit tangent and the unit normal, I probably already have the acceleration. The idea is this: as I'm moving around, I want to know what is the linear combination of the unit tangent and the unit normal. If I'm outside, last time I checked, there was no X, Y, and Z axes. So there's no orientation. So if I said I'm moving in a particular direction, well, what direction is your tangent vector pointing in? It's pointing that way. What direction is your normal pointing? It's pointing that way. I don't need specific values. I just need to know what direction they're pointing. So when we're doing this process, an answer might look something like this. I'm describing my acceleration, and my acceleration ends up being, 3/2 t plus 4n. That might be my answer. I never bother finding t and n because I already know a. I can work backwards to find t and n. But I might say, okay, so I have a little bit more in the normal than the, but I don't need to necessarily state what those values are. That's the point. I'm writing my acceleration as a linear combination of these two unit vectors. Now, that's not an unusual thing. For those who have had linear algebra, this is exactly what you do. If you had three vectors in three space that are not all pointing in the same direction, you do what's called the Gram-Schmidt Orthonormalization process to move them around to create a mutually orthogonal set of vectors. So I might have three vectors that are all pointed, let's say, towards you like this. So let's say that's my fixed vector. So then I rotate this one till it's at a right angle, and then I rotate this one till it's a right angle to both of them. And now I have three mutually orthogonal unit vectors. And now as I move around space, they're not necessarily going to be unit vectors on the X, Y, and Z axes. Oh, no. They're just going to be three unit vectors in space. But then I can describe any vector in space as being a linear combination of those three. Just like now we can describe any vector in space as being multiples of unit vectors on the X, Y, and Z axes. Okay. So with that said, the question is, how do I find these things? Well, let's look at the first really handy identity. Erase this. Okay. Going back to this statement right here. A equals AT T plus AN N. Again, these are coefficients. I know that A is made up of linear combination of these two vectors that are mutually orthogonal. So if I said, let me just kind of write them down. Let's say that right there represented AT, and let's say that represented ANN. I'm making them of different lengths. Okay, so maybe this is 10t and that's 6n, whatever, doesn't matter. So tell me about A. Well, A's got to be the sum of these two. So isn't that A? Now, what about the length of A? Remember, that's a unit vector. That's a unit vector. So this is a scalar multiple of the unit vector. This is a scalar multiple of the unit vector. So if I said, how long is this piece? It's exactly AT long. By the way, AT and AN can't be negative. That's not possible. How much am I going in the tangent direction? -5. No. I'm moving that way. Yeah, AT and AN can't be negative. That would be impossible. They can't. One of them can be 0. Okay, if I'm moving on a line or I'm moving on a circle. The length of this piece is AN because that's a unit vector. So can I say safely that the square of the magnitude of the acceleration vector is nothing more than this simple Pythagorean theorem. Because these vectors are unit vectors that are mutually orthogonal. The length of the acceleration vector is just a Pythagorean theorem. So this squared plus this squared equals the length of this squared. Now, the reason this is so handy is that this is usually going to be trivial. See, if I give you the r of t, you take two derivatives and now you've got your a. There's nothing clever. So finding the magnitude of a is actually one of the simplest parts of the entire process. When I calculate one of these, then I can use this Pythagorean relationship to find the other, or better, I don't like doing that because if one of them's wrong, they're both wrong. I like finding both of these and then using this as my check that I did it correctly. That's a better way to go. The problem is when you're finding two different things independently, but you find one and you find a relation to find the other, then they're either both correct or they're both incorrect together, and there's no way to check if they're both incorrect. But if you find them independently of each other and then use that relationship, then it either works or it doesn't. If it doesn't work, then they're both wrong. If it does work, they're both right, and you can now be certain. So I like using this as a check as opposed to as a method of solving. So now that we've seen the relationship, the question is now, how do I find AT and AN? Well, glad you asked. That is why you're here today. I'll be bringing all this stuff back. So if all motion can be described as a linear combination of the unit tangent and the unit normal, let's assume that I have already found dsdt. I've already found speed. Let's assume I've already found curvature. I've already found a few things. Well, if I've found dsdt, then the AT, the tangential component, is just the derivative of dsdt. So that's hopefully not a horrible thing. I mean, it might be a horrible thing. I don't know. Okay, so we know a couple things. So let's suppose, let's go back to the AN part. I just want to go back to AN. So what was AN again? Okay, AN is this. All right, that's not because I told you, that's what we found out that it is, which is this. But if you remember last day, what did I come up with for curvature? Do you remember that for curvature, I didn't tell you this, we derived this. Curvature was the magnitude of V cross A over the cube of the magnitude of V. We did this last day during the lecture. We derived this. I didn't tell you this. We discovered this during the process. So that means that this is simply the magnitude of V cross A over the magnitude of V. Oh, that is cool. See, if I replace K with this, a bunch of the V's. So this is the easiest of all the shortcuts. Maybe I found dsdt successfully and it was easy. In fact, it probably was easy. K, if you remember last day, K could be difficult. Unless I'm moving like on a helix or something, K was probably a bit of work to find. So this was the backdoor approach. This was the backdoor approach that I taught you to find K. That was an alternate way that made it very, very easy. So if K were difficult to find, I still have AN, but what if I want to find AN without finding K? Why should I have to find K first? What if I just want to find the normal component? I can go directly to this. And that is a beautiful shortcut. Or I'm sorry, I can go directly to this. That's a beautiful shortcut. And we're going to do a couple of examples where we deal with both of them. Now, what I'd also like to know, is there a shortcut for the AT? Because dsdt might not be trivial. It might be complicated. You say, how could it be complicated? If my R isn't really complicated, let's say R involves simple polynomials, then V is going to involve simple polynomials. Then the length of the V is going to involve the square roots of lots of sums of squares of polynomials. And now you want to take the derivative of that. That's AT. That can be really gnarly. So the derivative of dsdt, if I'm not moving on a circle, is probably not going to be your friend. Okay, so let's write down the following. Let's do V dotted with A. But let's use the alternate versions of each one of these. So let's use what we've already done earlier today. Let's replace V with ds dt t, right? That's length of V times t. We know that's true. We've already used that today. In fact, we did the derivative of this. Dotted with, and now let's do it in terms of the actual components. So this would be dotted with d squared s dt squared t, that's my AT, plus ds dt quantity squared k n, right? And this was the whole point of today's lecture, was getting that. So I have no doubt that that's a correct statement. I don't know where it's going, but I do know that it's correct. So what I want to do is say, what happens if I do this dot product? You know, what will that result tell me, if anything at all? Well, let's do it. Right here, I get ds dt, which is a scalar valued function, times d squared s dt squared. Okay, that is my AT, by the way. And then t dotted with t plus, okay, dot product is distributive. So this would be ds dt quantity cubed k t dotted with n. I don't know why I want to do the dot product, but we use the cross product to help us find curvature. Well, let's use the dot product, see where it goes. So this is V dot A if I break it down into tangential and normal components. Okay, so what's the big whoop here? Well, T dot N, it's 0. They're orthogonal. T dot T, that's 1. It's a unit vector dotted with itself. Ooh. So let me rewrite this statement right here. I think we might be onto something. This says V dotted with A equals speed, which I'm going to go ahead and write length of V again, because now it's convenient to me. That is A little t. That's what we called it. I'm sorry, that's what we call it right here. Doesn't this mean that AT equals V dot A over length V? And folks, we have another ridiculously simple shortcut. So it turns out, if you do not feel like taking the derivative of ds dt, because maybe that's not an easy thing, maybe that's complicated, I can also find the tangential component this way. So we have a way of finding the normal component involving the cross product, and we now have a way of finding the tangential component involving dot product. So let me put them side by side. These I refer to as the backdoors, because remember, the main definition of this was this. Again, that being length V squared. If it's convenient, you find them this way. If it's not convenient, you find them this way. This way is never going to be taxing. But it turns out I might have a situation, for example, I'm moving on to helix. That's one of my favorites. This is correct, but it will take longer, actually. That will be more direct. So I want to now do a couple of examples of doing some of these from beginning to end, and then representing our answers in a way, and I keep cutting my head off, I'm sorry, in a way that makes some sense to us. So there's a lot of questions that we can ask from something, but let's just start with something as basic as, I want to describe motion in 3 dimensions. So let's consider that, let me take something that's not too terrible. Let's see. Try to think of numbers that are not going to be awful. That'll work. So let R of t be 2t, 4t, and how about let's let's say 4t squared. Actually, you know what? Let me make it this. Let me make these squared. So 2t squared, 4t squared, 4t. What I want to do is find the, I want to do this. I want to write a as this. And let's just pick a random value at t equal 1. You know, it doesn't matter what value of t I pick. Let's just say at t equal 1. Okay, I could pick any real number, but what I want to do is have an answer that doesn't have any t's in it, just has numbers. So let's start the process. Okay, so the first thing I need to do is find the velocity vectors. That would be 4t, 8t, 4. Now, the acceleration vector will be important. Let's go ahead and find it now. We may or may not actually end up using this directly. If we decide we're going to do the dot product and the cross product, then we will need it. So this would be 4, 8, 0. Okay. At some point, we'll need to evaluate both of these at 1 if we're going to do the dot product cross product thing. That's okay. So the next thing is ds dt, which is the length of v, will be what? So that's squared, so it'd be 16t squared plus 64t squared plus 16 all under the root. That would be 80t squared plus 16 under the root. And it looks like I can pull out a root 16. And by the way, always reduce the roots if you can. Otherwise, your roots are going to get bigger and uglier and scarier and, you know, just all hell breaks loose. Okay. So if I pull out the root 16, this would be 4 times 5t squared plus 1. And in the long run, that will probably be easier to work with. Now, do I need to do any more derivatives? Yeah, because the first thing I want to do is I want to do the d squared sdt squared, because that's not a hard derivative to take. So d squared s dt squared, the derivative of this. So if it helps you maybe rewrite this in that form. So this would be 2 5t squared plus 1 to the negative 1/2 times 10t, which is 5t over the square root of 5t squared plus 1. Okay, so I got that. Now what? I could actually stop and not do any more derivatives at this point. That would be totally okay. AN will involve the curvature. Now think about that. The curvature means that I've got to find the unit tangent, take its derivative, make that into a unit. No, I don't want to find the curvature that way. In fact, I don't want to find the curvature at all. In this case, I want to find AN. So in this case, I'm definitely going to use that cross product thing. All right. But before we do the cross product thing, here's at this point in the problem, there are no more derivatives that I have to take. This is important. So at this point in the problem, I can evaluate everything I need at 1. Never evaluate at 1, or never evaluate prematurely, because if you evaluate early and you still have derivatives and things to do, remember, you're going to get zeros, and you don't want zeros when they're not supposed to be there. So let's put it over here. So v of 0 is what? V of 0 is simply 0, 0, 4. A of 0 is 4, 8, 0. Okay. D squared s dt squared evaluate. Oh, I'm sorry. You know what? What am I doing? It's not. I'm sorry. Not 0. 1. Oops. That would not have ended well. Sorry about that, folks. Because we're standing too close to the board. At 1, 4, 8, 4. Let's try that one more time. And at 1, I'm still 4, 8, 0. Okay. And now I want d squared s dt squared evaluated when t is 1. That's the proper notation. Vertical bar evaluated at. So I'm going to put a 1 in here. So what would that be? Looks like it's going to be 5 over root 6. Now that can't be simplified. If you want to rationalize it, that's fine, but there's not going to be any canceling taking place. Okay, so it appears that all the things I need to evaluate, I have. So now what we want to do is we want to do the dot product, we want to do the cross product, because I'm going to need all of those things. Trying to use different colors.
Professor?
Yes.
Real quick, could you read off the equation you have for d squared s over dt squared? My screen is just really blurry. I can't read that. Yeah.
Oh, well, I'm doing can you see this here?
Yeah.
I'm doing the derivative of this. I just brought the half, this to the negative half times 10t.
Yeah,
So
but I just don't, my screen's blurry. I can't read. Yeah, what does that say?
Oh, you know what?
Should there be a 20t?
You're right. So I'm glad you had a blurry screen, because that's 20t. 20t. Aha. Good catch. The thing is by the way, I don't ever make errors on purpose. I just make errors. But I was going to do the problem in such a way that we're actually going to have multiple opportunities to check. And this is critical. If you don't have ways of checking an answer, then you do all of this work and you say, I hope I'm right. I'm going to show you really, really simple ways to check and verify that everything you said works, including like the Pythagorean identity we did, so that there's no doubt. So if you get to a problem and it's not checking, you know you have an error. Finding the error isn't always easy. I didn't multiply these. I some reason did a half. So that should be a 20. Okay. Now that I can do something with that. I'm going to leave it alone. So now what we want to do, or we want to do a of 1 dotted with, or actually I'll write v. Sorry, it doesn't matter. It's dot product. I'm going to write v first. V of 1 dotted with a of 1 is what? 16 plus 64 plus 0. So that's 80. Let's do v of 1 cross a of 1. Okay. Negative 32. 16 minus 0. 32 minus 32. That's convenient. Okay. And the last piece of this that we need the magnitude of v of 1 cross a of 1. So the magnitude of that, so this squared plus this squared square root, or you can be really, really lazy. That's going to be 16 root 5. How did Mr. Brown do that in his head so fast? I factored out the 16, and then it's just negative 210, which is of length root 5. I'm lazy. I never actually use the whole numbers. I make it easy on myself. All right. We now have every possible thing we could possibly want in this problem, possibly. Okay. So what do we know is AT? We know that's AT right there, by the way. I may have to do some erasing later. We know AT is 20 over root 6. Now, yes, I can write that as 10/3 times root 6. I don't know that that's any better because my root's still the same. What is AN? So remember what I said AN was? AN was the quotient of this quantity. Actually, do we even have, I'm not sure we have it up here. We actually haven't evaluated this. So let's evaluate that guy. I said we were done. There was one more. I need the length of v of 1. Don't think we ever found that. So go to here. If I replace t with a 1, that's going to be 4 root 6. Okay, so I needed that piece. So AN, which I'm not going to find by finding curvature and all those pieces, I'm going to find using the length of the cross product over the length of the velocity, because that's just flat out easier. So it looks like it's going to be 16 root 5 over 4 root 6. Now that definitely can be simplified because a root in both numerator and denominator is considered not quite finished. So at this point here, I would probably do something like that. Now that's going to be 4 on top, 6 on bottom. So that looks like it's going to be 2/3 root 30. Okay, I'm not sure I can do any better than that. We are now finished. So wait a minute, finish with what? Well, we found all the things we have to find. Now we're going to write our final answer in this form. So our final answer is the acceleration vector, by the way, and I'm going to write of 1 because this equation that I'm going to write out is only true at t equal 1. If I had used t equal 2 or t equal 10 or t equal 1,000, I would have gotten different values for these guys. So this is 20 over root 6 unit tangent vector plus 2/3 root 30 n. Now, if you wanted to leave that root in the bottom, that would have been okay. You would have had 4 root 5 over root 6. And there's nothing wrong with that. In fact, that might have even been, let me write this. You could have written 4 root 5 over root 6. Same thing. Okay. And the only reason you might have done that is that way these both have the same denominator. So if I was actually multiplying things out, that might be more efficient. Now, that's my answer. How do I know if I did it right? Well, A of 1 is 480. 480. Yeah, but I don't know what T and N are. So knowing what A of 1 is, you have to understand, is not really helpful. I know what A of 1 is. But since I'm never even going to bother calculating the T or the N, I can. I just don't feel like it. So I want to know, is that correct? Here's the ultimate check. Remember the Pythagorean relation. That number squared plus that number squared must be the magnitude of that squared. Has to be. Absolutely has to be. So that's going to be our check. And the question is, where am I going to do it? Yes. Okay, hold on. I'll do it here. I hate erasing, but never going to fit that in otherwise. You notice that I didn't use the fact that I knew this one to help me find this one. I found them independently. And now I'm going to check them using the Pythagorean. If I had found them using the Pythagorean, that's not wrong. But if you make an error on the first one, that means every part of your answer is incorrect. And that's not good. All right, what's the length of A1? So, or let's do this way, make it simple. What's A1, length A1 squared? 4 squared plus 8 squared. Have we found that already? Something's not right here. I just realized something. I think we made a boo-boo. I think we did that one, didn't we? Anybody catch that? That 4 root 6? 4, oh, which one did we do? Or did we do this one? I don't even remember now. Length V1 should be 4 squared plus 8 squared plus 4 squared, which is root 96. Did we have that somewhere? Oh, yeah, we do. Yeah, we do. Never mind. I'm sorry. We did it over here. We're good. I was thinking that we hadn't done this yet. We did it right here. Okay, no, we're cool. We're cool. So length of this guy is 4 squared plus 8 squared. That's 80. So the length squared is 80. Okay. Question. I'm going to write in question form. Is that equal to 20 over root 6 quantity squared plus that's why I said leaving it in that form right now might have made it easier. I'm gonna put it in that form. 4 root 5 over root 6 squared. I'm gonna do that. That way they both have a denominator of 6 because I'm lazy. Well, let's see. That would be 400 over 6 plus 4 squared is 16. Root 5 squared is 5, so that'd be 80. And I have 480 over 6, which is 80. Crowd goes wild, confetti everywhere. People screaming, dancing in the street. Looks like that scene in World War II ends, you know, and then kissing the whole thing. Okay, that's my check. Here's the best part about that check. It's impossible that there's any error anywhere in the problem. That's my absolute confirmation that every single thing I did was correct, because no matter how small an error was, any error anywhere in the process, that would have been impossible to confirm. That's why I'd rather use the check at the end of the problem to confirm it. So earlier when I inadvertently had the wrong number there, that would have shown up in the check. Now, the problem is if the check doesn't work, it's not always easy to identify the error, but you know you have an error, so you can kind of backtrack. So our final answer is some version of this. We didn't find t, we didn't find n. That wasn't the point. That means my motion. Now, in terms of numbers, I have a calculator somewhere. In terms of numbers, 20 over root 6. Oops. Is about 8.1 something. 4 root 5 is a little more than 3.5. This number here is a little more than double this number here. What does that mean? That means that the tangent is more dominant than the normal. So in other words, I'm straighter than I am circular. That's all it means. Again, because that coefficient is more than double that coefficient. There's more pulling you in the straight direction than there is pulling you into the center of the circle. That's how you can interpret that. All right, let's do another one, but now let's do one with a helix, which is our favorite shape, and we'll see how easy most of these calculations turn out to be as a result. No part of this process was difficult, except the fact that I have a 3x4 whiteboard. That's the hardest part, trying to fit everything. When you're doing this pencil and paper, take all the room you need, because you don't want to make an error and then not find it because you squished everything in there. So let's do a simple helix kind of thing. Let me make one up. R of t is, how about, let's see, 2 cosine 6t, 2 sine 6t, and 16t. Okay, that seems reasonable. What I want to do, in fact, I'll make it even simpler. I want to find everything. I want to find every aspect of this. I want to find the unit tangent, the unit normal, the curvature, the tangential component, the normal component, every single thing we could possibly mention to describe this motion, quite frankly, because it's going to be really, really simple. Because this is circular in nature, it's a helix, it's doing this. There's no part of the process in any way that will be challenging. And the numbers are probably going to be very friendly. So here's my instruction. Find everything. And let's evaluate everything. When all is said and done, how about it t equals 0? And the reason is I don't want curvature, tangential component, and normal component to be in a function form. Those are things that are always scalars. You never finish a problem with a, t, a, n, or k being functions of t. You always say add a particular value of t. Now, the unit tangent, the unit normal, the acceleration, the velocity, all of those are going to be functions at t until I evaluate them, but I don't evaluate them until the end. So let's start. So v of t is negative 12 sine 6t, 12 cosine 6t, 16. The length of v of t is the square of this, 144 sine squared 6t, plus the square of this, 144 cosine squared 6t, plus the square of that. Okay, well, if I factor out the 144, that's 144 times sine squared plus cos, which is 1. So this is 144 plus 256, that's root 400 or 20. How nice that those numbers worked out so well. So now, what is my unit tangent vector? It's 1/20th of this vector. So negative 12/20, that'd be negative 3/5. And then 16/20 would be 4/5. And it's always a good idea to make sure that that's a unit vector. This squared plus this squared plus, yeah, I mean, if you do a quick check, it should turn out to be 1. All right. Now, I haven't evaluated anything at 0 yet. I don't need to. Well, I don't, because I got to take this derivative still. So dt is, now I need the derivative of this guy. So this is going to be negative 18/5 cos t, or excuse me, cos 6t. 18/5, sorry, negative 18/5 sine of 6t, 0. That clearly is not a unit vector, but it's also really easy to determine its length. If I factor out the 18/5, then I'd have a cosine and a sine making it a unit vector. So the length is 18/5, not negative 18/5. So this squared plus this squared square root, or just factor out the 18/5. That's the easier way of doing it. So finally, what is the unit normal vector? I'd multiply the reciprocal of this into here, and I would get negative cosine of 6t, negative sine of 6t, 0, which is a unit vector, which proves that is in fact the length. Now, before you take another step, n and t have to be orthogonal. If they aren't, then this is horribly wrong. So this squared plus this squared plus this squared equals 1. That is true. So now let's do a quick dot product between them. This is positive 3/5 sine cos. Negative 3/5 sine cos, 0. That does in fact add to 0. I've just proved that n and t are orthogonal. Clearly they're both unit vectors. That means we know at this point they are correct. That is not in doubt. Okay. We are now ready to finish the entire problem. Now things evaluated at 0. I'll put those up. In fact, I might even erase that later. So now how do I find a little t? Well, what is the length? By the way, this is also equal to ds dt. We know that the length of v of t is ds dt, and ds dt is a constant. So at, which is d squared s dt squared, which is d dt of length v, if you will, is 0. Can that happen? Yeah, it did. That means there is no part of this that uses the tangent direction. Now, I can do the a cross v. I can do the cross product and all that, but that's more work than I have to find the acceleration vector. I got to do extra stuff. I don't feel like it. I'm lazy. Let's find an. Now, we can find it using Pythagorean theorem, or we can find it by its actual formal definition. There's a different color here. Remember what an is. An is the length, it's ds dt quantity squared, or you can just say length of v squared times curvature. But what's curvature again? Curvature was the length of dt dt, which we have right here, over the length of v. Oh, so over the length of v. Oh, that means that one of them cancels. Oh, that makes it really easy. So my normal is 20. See if I did this right. Almost lost, hold on, lost myself there for a second. Yeah, there it is, 20, and then that's 18/5. So that's 72. 72. So right now, and, oh, I'm sorry, we never actually found curvature, did we? My bad. Curvature's sitting right there. Let me put curvature. I'm running out of room here. Curvature is length dt dt. I guess I could have done curvature first over length v, which is 18/5 over 20. And that would be 9/50 if I reduce that. So I've got my curvature, my tangential component, my normal component. So the final piece of the puzzle, I'm going to erase this because I don't think I need this to finish. I said I wanted everything at 0. So v of 0 is 0, 12, 16. A of 0 is, And we actually haven't found A of 0, have we? Oh, you know what? We never found A. Let's find A. I said everything. So A is the derivative of this guy. So that would be negative 72 cosine 6t, negative 72 sine 6t, 0. So therefore, A of 0, now I can put it in there, is negative 72, 0, 0. Capital T of 0 would be 0, 3/5, 4/5. N of 0, where's N? Here would be negative 1, 0, 0. And again, quick check, these are orthogonal and they are both unit vectors. K we said was 9 over 50. AT was 0. AN was 72. Now this is, we're done. There's absolutely nothing left we could pick apart. You say, how do I know I'm right? What's the length of the acceleration vector? It's 72. If I factor out the 72, right here. Look at this guy right here. A of 0, isn't that 72 times negative 1, 0, 0? If I factored out the 72. And isn't this 0 times my unit tangent plus 72 times my unit normal? That's beautiful. Everything worked because there were no mistakes. In this case here, doing the dot and cross products of the velocity and acceleration would have been perfectly correct, but they actually would have taken me much longer to get to the same place. This was actually easier to just do it directly. So you have two ways of finding everything now. And again, if it's fairly simple motion like this, then directly is probably easier, but you can still use the dot and cross product versions of A and T, excuse me, of A and V. That will always work. And that's probably never going to be difficult. So a lot of folks just say, you know what, I'm going to adopt that and make that my own. All right, we are now done